Hello everyone, welcome to this video lecture. This is Menaka from the Department of Chemistry. Today I am going to discuss about the topic Fundamentals of Electrochemistry under the course name Physical Chemistry. In this video, we are going to discuss about the basic concepts and terminologies in electrochemistry, migration of ions, transport number and Kohlrausch law. First, what is electrochemistry? Electrochemistry is the study of chemical reaction in which electrons makes a movement. The movement of electrons will give you the flow of electricity. Actually, this electrochemistry deals with the chemical reaction that takes place at the interface of electrode and the electrolyte. Here you can able to see the two electrodes. One is anode, another one is cathode. In which anode usually oxidation reaction will be taking place and in cathode reduction reaction will be taking place. So electrochemistry is also the conversion of electrical energy into chemical energy. We can able to witness the application of electrochemistry almost everywhere in our day-to-day life, starting from automobile industries to electroplating. So we all know that the flow of electrons will lead to flow of electricity. So the factor which is required to measure the ease of flow of ions through a solution is called conductance. It is given by the reciprocal of resistance. The terminology or the symbol used for conductance is G. G is given by 1 by R. The unit of conductance is Siemens or mho. Now let us see what is specific conductance. Before that, we want to know what is specific resistance. Resistance of a conductor having a length equal to 1 centimeter and area of cross section 1 centimeter square. Here we can see the mathematical expression R is equal to rho into L by A, where L is the length and A is the area of cross section. Here it can be rewritten as rho is equal to R into A by L. Now we can see what is specific conductance or conductivity. Specific conductance is the reciprocal of specific resistance, which is given by the symbol kappa. Kappa is equal to 1 by rho. It can also be rewritten by using the specific resistance value, that is L by A into 1 by R. From the previous equation, we know 1 by R is nothing but conductance. So the unit of specific conductance is given by Siemens per meter. Usually, this conductance and specific conductance is used for characterizing the metallic conductors. But for the electrolytic conductors, we need a separate terminologies, namely equivalent conductance and molar conductance. What is equivalent conductance? The conductance of all the ions produced by 1 gram equivalent of an electrolyte in a given solution. It is represented by the symbol lambda equivalent, which is equal to specific conductance kappa into volume of solution in cc containing 1 gram of electrolyte, that is V. The unit of equivalent conductance is centimeter square, Siemens centimeter square per equivalent. Now let us see what is molar conductance. Molar conductance is nothing but the conductance of all the ions produced by 1 mole equivalent of the electrolyte in a given solution, which is given by the symbol lambda m, equal to specific conductance kappa into volume of solution in cc of solution containing 1 mole of electrolyte. Now let us see what is the relationship between the kappa specific conductance and equivalent conductance lambda equivalent. For that, now we can consider that 1 cubic meter solution is immersed in between two electrodes separated by 1 meter length and 1 meter square area of cross section. Now what will be the conductance? The conductance will be equivalent to specific conductance because the two electrodes are separated in a specified area. Now we can consider this 1 cubic meter solution will contain 1 gram equivalent of the electrolyte. Now what will be the conductance? The conductance will be equivalent to equivalent conductance because the 1 cubic meter solution containing 1 gram equivalent of the electrolyte. So in this equation, we can equate the conductance is equal to specific conductance kappa, which is equal to the equivalent conductance. Now again, we are considering another case that we are diluting this 1 cubic meter solution into a 1000 cubic meter solution. Then what will be the conductance? Now the conductance will be equal to 1000 times of its specific conductance. So this is the relation between the specific conductance kappa and equivalent conductance. Now let us see how the dilution affects the variation of conductance and specific conductance. So now we are increasing the dilution of the electrolytic solution. Now what happens? The degree of dissociation increases. That means more and more number of ions will be produced in the electrolytic solution. So which in case the ease of flow of electricity will be more. So that means the conductance of solution is getting increased. On the other hand, if we look into the specific conductance, majorly the specific conductance is depending on the number of the ions per cc. So in that case, the specific conductance will be getting decreased. So what happens to the other molar conductance and equivalent conductance? Obviously, they also will be getting increased. Now, let us see the equivalent conductance at infinite dilution. What is that equivalent conductance at infinite dilution? The tendency for the equivalent conductance to approach a limiting value when the concentration approaches zero. That means at higher dilution. Whole of the electrolyte has been ionized. Even if you add the further amount of water into the electrolytic solution, it will not bring any change for the equivalent conductance. In that case, that particular dilution is said to be infinite dilution. See, in this figure, you can notice that for a strong electrolyte like potassium chloride, we can able to calculate the equivalent conductance at infinite dilution by extrapolating. But in case of weak electrolyte like acetic acid, we cannot able to calculate the equivalent conductance at infinite dilution because the extrapolation will give you maybe a insufficient data. But in that case, we can go for an indirect method called application of Kohlrausch law that will be explaining in the upcoming slides. Next, we'll see what is ionic mobility or migration of ions. So we have learned that at infinite dilution, all the electrolytes are completely dissociated. But there is some difference in the molar conductance value. What is the reason for this molar conductance value difference? The difference is because of the speed of the ions. Now let us take the example of the molar conductance of HCl and NaCl. If we look at into the value of molar conductance of HCl and NaCl, the value of HCl is found to be 3 times greater than NaCl. This is because of the speed of the H plus ion is found to be more than the speed of Na plus ion. So this is due to the ionic mobility. So ionic mobility as a definition is given by distance traveled by an ion per second under the potential gradient of 1 volt per meter. Now let us see what is the reason for the low ionic mobilities of this lithium ion and sodium ion. We all know that lithium ion and sodium ion have smaller radii and it also has higher charge density. So in that case, because of the high charge density, they will be highly hydrated due to dipole interactions. So in that case, what happens? It is very difficult to mobile through the electrode along with the shell of the water molecule. So that is the reason for the less mobility of sodium ion and lithium ion. Now, let us see what is the reason for high mobility of H plus ion. So, usually this H plus ion has high mobility and high migration capacity when compared to other ions. The high mobility in hydroxylic solvents such as water can be explained by this Grott's type mechanism, in which this proton of hydronium ion will be moving rapidly to a hydrogen bonded water molecule and is transferred further along the series of hydrogen bond water molecules by the rearrangement of hydrogen bonds. So this is the reason for the high mobility of H plus ion in the water molecules. Now, let us see what is transport number. We all know that the flow of electrons or the flow of ion will lead to the flow of electricity. So, from this, how we can calculate the transport number? The fraction of total current carried by the cation or the anion is termed as transport number or Kirchhoff's number. Now, the mobility of cation will be denoted by the symbol U plus and the mobility of anion is denoted by the symbol U minus. Now we can calculate the transport number of the cation by using the formula T plus is equal to current carried by the cation divided by total current. In mathematical expression, we can give this equation as U plus divided by U plus U minus. Okay, next we can see how to calculate the transport number of the anion, which is termed as G minus. That is also given by the formula current carried by the anion divided by total current, which is also given by the mathematical expression U minus divided by U plus U minus. And we can also calculate the transport number if we know the transport number of any ion. We can easily calculate the other ion by using this relation T plus G minus is equal to 1. So this is the relation between the transport number of anion and cation. Now we are coming to the Kohlrausch law. So we all know that at infinite dilution, when dissociation is complete, each ion will make a definite contribution towards the molar conductance of the electrolyte, irrespective of the nature of the other ion. So in that case, so according to the Kohlrausch law, the molar conductance at infinite dilution for any electrolyte is given by the sum of the contribution of the two ions. So which is given by the formula lambda naught m, that is molar conductance at infinite dilution will be equal to sum of molar conductance of individual ions, that is lambda plus naught and lambda minus naught. That is, what is lambda plus naught? That is contribution of cation towards the molar conductance at infinite dilution. Similarly, lambda minus naught is nothing but the contribution of anion towards the molar conductance at infinite dilution. So this is the Kohlrausch law. So what is the application of Kohlrausch law? So before going into the application of Kohlrausch law, let me explain the importance of the contribution of the anions and cations towards the molar conductance at infinite dilution by taking some examples having same pairs of anions and cations. See, in the tabular column you can see this is a pair of electrolytes with the same anions and same cations. See here, so first let us take potassium fluoride and sodium fluoride. Here you can have both the anions are same, that is fluoride. So this is the corresponding value of molar conductance. The difference between these two values is given by 23.42. That means what? If you replace the potassium ions by sodium ions in any electrolyte, always it will produce the same difference of 23.42 in the molar conductance at infinite dilution. So that means according to the Kohlrausch law, the molar conductance at infinite dilution will be contributed by individual anions or cations. So now let us see what is the application. So previously I have told you that we cannot calculate the molar conductance at infinite dilution for weak electrolytes. So in that case we can use this application of Kohlrausch law for calculating molar conductance for weak electrolyte. So by calculating the individual molar conductance value, we can able to calculate this value for weak electrolyte. Also, we can calculate the molar conductance at infinite dilution of a sparingly soluble substance. So this is the application of Kohlrausch law. So in a nutshell, in this video, we have learnt about the basic concepts and terminologies in electrochemistry, like what is conductance, what is specific conductance, molar conductance, and so on, and how does it varies with the dilution. And we have learnt about the reason for high mobility of hydrogen ions and also the reason for low mobility of lithium ions and sodium ions, and how to calculate the transport number and what are the applications of Kohlrausch law. So thank you for watching this video. Thank you.